NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto, a remote and mysterious world, was once a singular and solid planet inside our planetary group. However, recent discussions among leading astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have pushed Pluto back into the spotlight with astounding discoveries. These researchers have suggested that Pluto's orbit may ultimately converge with Neptune's, a thought that raises questions about how such a collision could happen and what the consequences of such a massive event could be. Could this lead to a fascinating and strange anomaly, or is there more to this potential planetary crash? Join us as we dive into the possible outcomes of a Pluto-Neptune collision. Pluto, once thought to be a planet in its own right, is now relegated to a smaller category, thanks to its unusual orbit and its status as a dwarf planet. Despite its demotion, Pluto remains a subject of interest and research within the scientific community. Recent examinations by leading astronomers show that Pluto's orbit is dangerously close to Neptune's, raising alarms among astrophysicists like Tyson and Kaku about the possibility of a catastrophic collision between the two. But how could such a crash happen? Unlike the other planets in our solar system, Pluto follows an eccentric path around the Sun, taking an astonishing 248 years to complete one full orbit. Since its discovery in 1930, Pluto has not even completed a single orbit around the Sun. However, the intrigue surrounding Pluto doesn't end there. Its orbit is characterized by a highly elliptical shape, unlike the nearly circular orbits of the larger planets. What makes Pluto's orbit even more puzzling is its tilt. Pluto's orbit is inclined at an angle of 17 degrees to the plane of the solar system, which adds complexity to its orbital dynamics. This tilt, combined with its irregular shape, makes Pluto's orbit significantly more chaotic compared to other planets. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For approximately 20 years of each orbit, Pluto actually comes closer to the Sun than Neptune, which contradicts what one might expect based on their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets in the solar system. When Pluto's orbit was first studied after its discovery, astronomers struggled to understand its unusual trajectory. Unlike the orbits of other planets, which lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and elliptical shape. The mystery surrounding Pluto's orbit deepened when it was observed that Pluto's path indeed crosses Neptune's. This apparent paradox is resolved by the complex gravitational dynamics of the solar system, specifically through a phenomenon known as the three-body problem. The three-body problem in astronomy refers to the challenge of predicting the motion of three objects, such as Pluto, Neptune, and the Sun, that influence each other through gravitational forces. The interactions between these objects create a dynamic system that is difficult to predict, as each body affects the others in a constantly changing manner. For Pluto, the three-body problem explains why its orbit remains stable despite crossing Neptune's path. One key concept that keeps Pluto's orbit stable is libration. In Pluto and Neptune's case, this term refers to the phenomenon where, whenever Pluto crosses Neptune's orbit, the two planets are always at least 90 degrees apart. This spatial separation is crucial in preventing a collision. Another significant factor is vertical libration, which refers to the up and down movement of a celestial body within its orbit. For Pluto, this means that when it comes close to Neptune or another large planet, it remains positioned well above or below the plane of their orbits, adding another layer of protection against potential impacts. A third concept that stabilizes Pluto's orbit is VZK wobbling, named after the three scientists, VKL and O, who studied how celestial bodies move in space. This phenomenon describes how Pluto, Neptune, and the Sun influence each other through gravity, causing slight shifts in their positions over time. In Pluto's case, VZK wobbling explains why its orbit, despite seeming chaotic, remains stable. These forces help maintain Pluto's orbit for incredibly long periods, possibly even billions of years. Although Pluto's orbit is chaotic by nature, these gravitational influences from other planets help keep its trajectory stable within the broader context of the solar system. These forces play a fundamental role in preventing planets and other celestial bodies from colliding with one another. Without these stabilizing factors, the solar system would be a much more chaotic place, with planets and dwarf planets potentially colliding or being ejected from their orbits, triggering a cascading series of effects. For Pluto, this stability is particularly important, given the ongoing discussions about a possible collision with Neptune. Understanding Pluto's orbit provides insight into the dynamic nature of the solar system. It serves as a reminder that even the most seemingly unstable orbits can achieve a state of balance through the intricate dance of gravitational forces and orbital mechanics. The study of Pluto's orbit also highlights the need for continuous research and observation to better understand the forces shaping our solar system. Pluto's case illustrates the importance of studying the unpredictable nature of celestial bodies and the role gravitational interactions play in their movements. The concept of orbital resonance, referring to the delicate balance of gravitational forces governing the orbits of celestial bodies, is clearly demonstrated by Pluto. Even small changes in its position or speed can significantly alter its long-term orbit. In the late 1980s, virtual simulations provided valuable insights into Pluto's orbit. These simulations showed that despite the stabilizing effects of phenomena like libration, Pluto's orbit can still be highly unpredictable. A tiny deviation in its initial conditions, such as its position or velocity, could result in dramatic changes in its trajectory over millennia. Despite this inherent unpredictability, these models also showed that Pluto's orbit remains relatively stable over billions of years, suggesting that its journey around the Sun follows an underlying order, even if it appears chaotic. However, these simulations also revealed the challenges of making precise long-term predictions. The three-body problem, combined with the sensitivity of the system to initial conditions, makes forecasting Pluto's future trajectory a complex and uncertain task. Although simulations provide a useful tool for understanding and predicting the behavior of celestial bodies, they are limited by the accuracy of the initial data and the complexity of the forces at play. These challenges are further emphasized by the fact that celestial orbits like Pluto's tend to be turbulent and difficult to predict. Pluto's orbit serves as a reminder of the ever-changing and dynamic nature of the universe. While we have made significant progress in understanding space, Pluto's case demonstrates how much we still have to learn about the gravitational influences of the giant planets, such as Jupiter, Neptune, and Saturn, and their role in shaping Pluto's orbit. This brings us to the question: why are prominent astrophysicists like Neil deGrasse Tyson raising concerns about a potential impact between Pluto and Neptune, despite the many complex forces working to prevent such a scenario? Tyson, a renowned astrophysicist who played a significant role in Pluto's reclassification from planet to dwarf planet, offers an insightful perspective on the evolving nature of celestial mechanics. He argues that while Pluto's orbit is stable for now, it may undergo massive changes in the future. This possibility underscores how much more we still need to discover about the forces that govern our solar system. Tyson's views on Pluto's reclassification and its current status as a dwarf planet are rooted in our ever-expanding understanding of the solar system. He believes that this reclassification is not a demotion, but rather a necessary adjustment to our growing knowledge of the cosmos. Different bodies circle our Sun. Tyson's way of dealing with divine mechanics is one of progressive learning and change. He recognizes the intricacies of Pluto's orbit and its connections with Neptune while perceiving the inherent unpredictability of space. He proposes that while Pluto's orbit is stable right now, it could undergo tremendous changes in the future, serving as a reminder of the dynamic and ever-evolving nature of our understanding of the universe. Tyson's perspective highlights the inherent uncertainty in space exploration and celestial mechanics, emphasizing the need for continuous study and adaptation in the face of new discoveries. He points out that, despite Pluto's orbit being relatively stable for billions of years, there is always the possibility of unforeseen changes. As we delve deeper into the forces acting on these distant bodies, the complexity of Pluto's relationship with Neptune serves as an excellent example of how even well-understood orbital dynamics can be subject to future modifications as our knowledge expands. Furthermore, Tyson's observations on Pluto's orbital resonance with Neptune, where Pluto completes 2 orbits for every 3 of Neptune's, demonstrate how delicate and finely tuned the mechanics of the solar system are. This resonance maintains Pluto's stability by preventing it from coming too close to Neptune, a crucial factor in the continued security of both planets. However, Tyson's concerns stem from the fact that such dynamic systems can still be vulnerable to changes, especially over long-term scales. While Pluto's current trajectory suggests that a collision with Neptune is highly unlikely anytime soon, Tyson reminds us that cosmic events and celestial movements are ongoing, and nothing is set in stone. The broader implications of this idea are significant. Tyson suggests that the possibility of Pluto and Neptune's paths interacting unpredictably highlights the complexity and uncertainty of the universe. Even with all the forces working to keep planetary orbits stable, there are always factors that could alter their trajectories. This recognition of uncertainty and dynamism is fundamental in the scientific exploration of space, as it drives ongoing research and technological advancements in astronomy. Understanding the mechanisms that keep planetary bodies in their orbits, as well as how they may shift over time, is crucial to comprehending the broader structure of the solar system and beyond. Likewise, Tyson's involvement in the reclassification of Pluto, from a planet to a dwarf planet, reflects the evolving nature of scientific classification. The decision was not based on diminishing Pluto's significance, but rather on a more nuanced understanding of what constitutes a planet. As our knowledge of the solar system has expanded, we have recognized that Pluto does not meet the criteria for a full-fledged planet, primarily due to its smaller size and irregular orbit. However, Pluto remains a fascinating object of study, providing insights into the outer reaches of the solar system and offering a window into the history of planetary formation and evolution. Michio Kaku, another renowned astrophysicist, shares similar views regarding the complexities of Pluto's orbital dynamics. Kaku is known for his work on string theory and his ability to explain complex scientific concepts in an accessible way. In his discussions about Pluto and its interactions with Neptune, Kaku emphasizes the importance of considering the broader context of the solar system's formation. He points out that the solar system is not a static, unchanging entity but rather a dynamic and evolving system. Just as gravitational forces between planets shape their orbits today, they will continue to do so in the future, potentially in unexpected ways. Both Kaku and Tyson acknowledge the role of advanced computational simulations in helping scientists model and predict the behavior of celestial bodies like Pluto. These simulations, which use complex mathematical algorithms to calculate the gravitational interactions between different planets, are crucial for understanding the long-term stability of planetary orbits. However, Kaku also notes that while these models are valuable, they are not foolproof. The inherent complexity of the three-body problem and the sensitivity of orbital dynamics to initial conditions mean that predictions about the future behavior of planets are always subject to uncertainty. As we continue to study Pluto and other distant objects in the solar system, we are also forced to confront the limits of our current understanding. The more we learn about these celestial bodies, the more we realize how much there is yet to discover. Whether Pluto and Neptune might ever collide is just one example of the many mysteries that remain. While the scientific community has made great strides in understanding the forces at play within our solar system, there is still much to explore. The ever-changing nature of space serves as a reminder that our knowledge is always evolving, and there will always be more questions to answer. This dynamic approach to understanding space and planetary mechanics is reflected in ongoing research and technological advancements. The study of Pluto and its interactions with Neptune provides valuable insights into the broader mechanics of the solar system and the universe as a whole. The complexity of these systems, while challenging, also opens up exciting possibilities for future exploration and discovery. As we continue to observe Pluto's orbit and the gravitational interactions between planets, we gain a deeper understanding of the forces that govern the universe, helping us better comprehend our place within it. The potential collision of Pluto and Neptune is just one aspect of the larger, more intricate picture of the solar system. The influence of other giant planets like Jupiter and Saturn cannot be ignored, as their gravitational effects play a crucial role in shaping the orbits of planets like Pluto. Jupiter, for instance, acts as a sort of cosmic protector, its massive gravity helping to stabilize Pluto's orbit and preventing it from being ejected from the solar system or colliding with other planets. Saturn, too, plays a role in maintaining the delicate balance of the solar system, with its own gravitational influence contributing to the overall stability of the outer planets. In other words, Pluto's orbit may seem small and insignificant, but it is a crucial piece of the puzzle that helps us understand the broader dynamics of the solar system. The study of Pluto and its relationship with Neptune and other planets provides a window into the complexities of planetary formation, orbital mechanics, and gravitational interactions. By examining these celestial bodies, we gain insights into the fundamental forces that shape the universe and are reminded of the constant interplay between order and chaos in the cosmos. As scientists continue to study Pluto's orbit and the forces that govern its motion, we can anticipate new discoveries and insights that will deepen our understanding of the solar system and beyond. While the likelihood of a future collision between Pluto and Neptune may be low, the very idea of such an event serves as a reminder of the unpredictable and ever-changing nature of the universe. Whether studying the farthest reaches of the solar system or exploring the mysteries of space, we are constantly learning and adapting our understanding of the universe, always striving to uncover the unknown and answer the questions that have yet to be asked. Pluto's case serves as a powerful reminder of the need for continued curiosity and exploration. While the paths of celestial bodies may appear fixed and predictable, they are always subject to the forces of nature, which can lead to unexpected and sometimes dramatic changes. As we learn more about Pluto and its interactions with Neptune, we are reminded of the delicate balance that governs the solar system, and the vast, mysterious universe beyond. With each new discovery, we come one step closer to understanding the forces that shape the stars, planets, and perhaps even our own place in the cosmos.